Welcome. We are trying to understand variational calculus. So, we will start with differentiation. What is differential? Suppose if you have a function, right, y as a function of x, so that is some curve. Now, when we take derivative, what we do is that we take a small change in x and find out what is the corresponding change in y, and dy by dx is basically said to be the differential, right. This is the process of differentiating. On the other hand, when we are looking at variation, what we are looking at is that we are looking at the same x value, but we are looking at curves which have different slope at the same x value and different y at the same x value. So, basically we are looking at for example, there could be another thing which goes like that. So, at the same x value it has a different y value and it has a different slope. So, you can also consider another function which is like that, which means at the same x value it has a different y value and it has a different dy by dx value. So, these are known as variations. So, in other words, when we are looking at variation, okay, no change in x. So, we are going to look at the same x value. At the same x value, we are looking at functions which have different y and dy by dx value at that point. So, that is why y and dy by dx become the independent variables, and we are trying to look at what happens to these things. So, at these points where for the same x the y and the dy by dx are not changing, are said to have no variation, right. There is zero variation on at these 2 points. Okay. Those are our x1 and x2 points in our definition yesterday. So, there is a way to make it more formal. So, like we say dy by dx, the d by dx which is the differential. So, similarly we define what is known as a delta operator, and delta operator operating on I, for example, is nothing but the varied I minus the original I. Okay. Now, we define this delta operator in such a way that it obeys certain properties, and one of the properties is that if you take delta of dy, then it is the same as d of delta y, that is the variation on the differential is the same as the differential on the variation. Similarly, we also define delta acting on y dx integral is nothing but integral of del y dx, that is the variation on the integral is nothing but integral on the variation. So, if these sort of properties are fulfilled, then we can define what is known as a delta operator, and the derivation that we are going to do using the delta operator is the same as what we did in the last lecture for obtaining the variation, except that we are making the process more formal, and hence it becomes we probably you have done it when you did the derivative. Initially the derivative is defined as a limit some h tending to 0 f of x plus h minus f of x divided by h, and every time you want to take the derivative of a given function, then you have to evaluate this quantity and then you have to find out what the derivative is. But after a while, then we come up with formula like d by dx of sin x is this, or d by dx of x squared is this, and so on and so forth. So, it becomes more mechanical. In a similar fashion, it is possible to make the process of taking variational derivative a little bit more formal, which is what I want to do. So, the derivation proceeds identical to what we did in the last class, except that the notation and the terminology we use is a little bit different from what we did. So, in that process, so let us take the original functional that we considered yesterday and try to do the variational derivative. So, what is the functional we considered? We considered I is equal to integral f of x y y prime dx. Okay. So, we want to consider we want to define as the variation on y delta y is nothing but y tilde minus y. Okay, y tilde are the varied paths. Remember, we had one optimizing path which was identified as y, and all the varied paths about that were basically defined by y tilde. So, y tilde minus y is delta y. So, delta y prime, and now because we also have all this commutation between delta and d, so also has this property. So, it is y tilde prime minus y prime. Okay. So, we now look at f. So, let us take f x y plus delta y prime plus delta y prime. What is this quantity? So, we are going to Taylor expand like earlier. So, it is x y prime plus dou f by dou y delta y plus dou f by dou y prime delta y prime plus higher order terms in delta. Okay. Now, if we take this, so f of x y plus delta y comma y prime plus delta y prime minus this f of x comma y prime, we are going to call this as the total variation on f. Okay. So, now what is this total variation on f? By the expansion that we have written, we can see that delta total on f is nothing but dou f by dou y delta y plus dou f by dou y prime delta y prime plus order of delta squared. Now, I am also going to define what is known as the delta total acting on I, which is nothing but the, so we have to integrate between x1 to x2, and so we had this f, so x y plus delta y prime plus delta y prime dx, right. So, this is what we are going to call the total delta I. So, that is nothing but delta. So, this quantity if I call as delta 1 of f plus order of delta squared. So, this quantity delta total of I is nothing but an integral x1 to x2, which is delta 1 of I. Okay. So, what is the delta 1 of I? So, the first variation on I is nothing but x1 to x2 dou f by dou y delta y plus dou f by dou y prime delta y prime integrated over dx. Okay. So, the delta total of I is nothing but delta 1 of I plus order delta squared, and delta 1 of I we identified with this delta 1 of, because this is delta total of f. So, this is delta 1 of f order delta squared. So, delta 1 of I will be this integral. Now, we can do now the integration by parts on this quantity. So, we have delta 1 of I should be equal to 0, which is a necessary condition. So, that means x1 to x2 dou f by dou y delta y minus, delta and d are interchangeable. So, when we, so let me write the first the full quantity and then we will do that delta y prime dx. So, which I am going to write as integral x1 to x2 dou f by dou y, delta y I am going to write outside, and dou f by dou y prime delta y prime. So, d and delta are interchangeable. So, I am going to make it as d by dx of delta y, and that d by dx I am going to bring on to this side by integration by parts. So, that gives me minus d by dx of dou f by dou y prime dx, and this integration by parts we do, we also have an extra surface term which is nothing but dou f by dou y prime delta y evaluated at points x1 and x2, and the variation delta y is 0 at the x1 and x2. So, we are going to take this quantity off. Remember, it need not be 0, you still have dou f by dou y prime to be 0 on x1 or x2 is sufficient. We will look at that case with respect to the action principle that we derived just now at the end of this derivation. So, if this quantity becomes 0, then we know that this should be equal to 0 because the first variation should be equal to 0. And the same argument as earlier works, because this delta y is an arbitrary variation in y, and this total integral from this x1 to x2 should be 0, then within that domain this should be identically equal to 0, which is basically the Euler-Lagrange equation that we have derived. So, we have this dou f by dou y minus d by dx of dou f by dou y prime should be equal to 0, and that is the so called Euler-Lagrange equation. This is what we derived, and we derived this in the last lecture. So, we have done the same thing, except that we have used this so called delta operator formalism. Now, let us go back to the term that we made 0 on the surface. So, that term was dou f by dou y prime delta y at x1 and x2. So, let us consider this quantity with respect to the action principle that we were looking at. In the case of action, what is this quantity? So, this quantity was something like this, and this was delta x, right. So, at these T1, T2. So, this delta x then is the variation in x, variation in position. So, this is, if you make this equal to 0, that is equivalent to prescribing the position at the time T1 and T2. So, this is or prescribing the position or displacement boundary condition. So, you can prescribe them, then in which case there is no variation allowed at time T1 and T2 at these points. So, they will become 0. On the other hand, you do not have to prescribe the position, you can expect this dou f by dou x dot to be prescribed, and if you look at that quantity, that is nothing but the force at that point. Okay. So, you can also prescribe the force at any given point. You can't give both at the point. So, either you can prescribe a force or you can prescribe a displacement at a given point. In either case, prescribing them makes this term on the surface to go to 0. So, you get the Euler-Lagrange equation. So, this becomes very important. There is a nice textbook by Shames and Dim called Energy and Finite Element Methods. In structural mechanics, I think. So, which basically deals with the boundary conditions that one can naturally derive from the variational calculus. Okay. So, in any case, so if you assume that your variations are prescribed at the end points, you can assume this quantity to be 0. So, you get the Euler-Lagrange equation, which is what we derived in the last lecture also. So, this is the variational derivative. So, basically variational derivative or the Euler-Lagrange equation is the first variation on the functional that we are considering. So, this brings us to the question as to why in the case of Hess-Wheel modeling we need to deal with variations. Why is it that we are dealing with functionals and not with functions? Okay. So, that is what we will discuss in the next part of this lecture. Thank you.